So we looked at how to make compound interest calculations using this formula. But what happens if the amount of times that we're compounding n, what happens as that gets very, very large? What happens as n goes to infinity? To investigate this, let's pretend that we're investing $1. And we found this really good bank that pays 100% interest. So our R is 1. That's pretty wicked good, right? And we're going to invest it for, let's say, 1 year. So the exponent becomes n also. So our amount would be 1 times 1 plus 1 over n to the n. We're saying $1 invested. Our interest rate is 100% wicked good. And it's for 1 year. How much money do we have? So let's look at what happens to this as n gets infinitely large. And to do that, we're going to use our graphing calculator. And so what I did is I graphed 1 plus 1 over x raised to the x. And what we can see is that it seems to be leveling out here as we go. And if we look at a table of values, as we roll down here, here we go. So remember, this means that we're getting paid interest 238 times every year. And what we see is that we're not growing very much here. So I passed my daily compounding. And if I continue going like this, what this is actually approaching, and there's a much more rigorous way to do this, but what I'm actually approaching is a very special number known as E. It's called Euler's number, and it's approximately 2.718. So, as we look at 1 plus 1 over n to the n, as n goes to infinity, in other words, the limit as n approaches infinity of 1 plus 1 over n raised to the n power is equal to this number E. It's similar to pi. It is an irrational number. It goes on forever, never repeats itself, and it's also called a transcendental number. This number is not the solution to any polynomial there is. So why do we care? Well, let's talk about compound interest again. Let's back it up to this formula. What if we were compounding continuously? So we're not getting paid interest every month, or every day, or every minute, or every second, but we're continuously getting paid interest. Kind of a crazy idea, but look at what this can become. So let's let m equal n over r. And you might be thinking, well, why in the world would I want that? Well, just bear with me. Look at what happens. This formula becomes p times 1 plus 1 over m. And then in the exponent, we have m times r times t, because n is m times r from this relationship. Okay, so what good does that do me? Well, watch. A equals p times 1 plus 1 over m raised to the m power, and raised to the RT. And we just got done talking about what happens as m goes to infinity. As m gets huge, as n got huge, m also would have to get huge, because we got a really, really bigger and bigger and bigger and bigger number over a constant. So as n goes to infinity, as n got huge, m also would be getting huge. So what does this become? Well, it becomes E. So A equals P times E to the RT. And you've probably seen this formula before, but this is where it comes from. As we're compounding continuously, as we're approaching infinity with n, this formula becomes P times E to the RT. what you have to pay attention to as you're reading problems is looking at how things are being compounded. Is it being compounded continuously at 5% or simply compounded at 5%? Compounded continuously, we are using PERT. Compounded at 5%, we're using our formula back here. So that's all this section is about. It's about involving E and then relating it back to this formula here, and noticing that you're going to make a little bit more money in the long run if it's compounded continuously, or the population will be a little bit bigger if it's compounded continuously over time.